-8 squared is 64, which is even. This says -8 should be even, which it is. But this is a totally different statement from this. This says if the square of a number is even, that number itself is even. This says if I start with an even number and square it, I get an even number. Those are not the same statement. Does everybody see that? If this is our statement, what do we call this statement? Remember the name for it? So this is called the converse, right? This is the converse of that. That's the converse of this. And a proposition and its converse are generally not the same thing. They're not going to be equivalent to each other in the general case. So if we were to prove this, if n is even, then n squared is even, we have not proven that. If n squared is even, n is even. They're different propositions. So we need to go about trying to prove this on its own. And there's ways we could attempt this using what we did before. We could say n squared is even. And so n squared equals 2 times k, where k is an integer. And then n equals the square root of 2k, where k is an integer. But it's really not clear where we go from there. How do we show that n itself is twice an integer? We've shown that it's an integer square rooted times the square root of 2, but that doesn't really help us. And it's not clear how, if we start off with this, n squared is twice an integer, we can get down to showing that n equals 2 times some other integer. So a direct proof kind of dead ends pretty quickly. But an indirect proof is going to work pretty nicely. So step 1, n squared is even. That's the hypothesis. Step 2, I'm going to say n is odd. And that's the negation of the conclusion. So I'm doing an indirect proof. I'm assuming that n squared is even, but this is not true, that n is actually odd, and I'm going to find a contradiction. So n equals 2k plus 1. Well, let me be precise. There exists an integer k such that n equals 2k plus 1. That's the definition of even. Definition of odd and proposition 2. So an odd number is twice an integer plus 1. And then I'm going to say n squared equals 2k plus 1 squared equals 4k squared plus 4k plus 1 equals 2 times 2k squared plus 2k plus 1. And that's algebra that I may have done once or twice before, but you can work through it more slowly and convince yourself this is right. And then we're going to make the statement 2k squared plus 2k is an integer. Anybody remember the reason we used for that? How can we say that 2k squared plus 2k is an integer?
That's what I said. Here. And I think it's the only one. That's literally what it was. Yeah. Because it wouldn't, because it can't attach to where the tertiary carbon is.
I don't know if that was an answer or if that was unrelated.
Closure of integers?
There we go. Closure of integers. Thank you. So the fact that in proposition 3, we stated that k is an integer, And we know that integers are closed under addition, multiplication, subtraction. If we take k, multiply by itself, multiply by 2, multiply by 2, add those together, we still get an int. Right? So whole numbers combine to give you whole numbers as long as you're not dividing. So we can state that this thing is an integer. And now what have we done? We've shown that n squared is twice an integer plus 1. That means n squared is odd. That's the definition of odd combined with 4 and 5. And have we reached a contradiction? Yes. We've reached a contradiction between statements 1 and 6. Statement 1 said n squared is even. Statement 6 said n squared is odd. That's a contradiction. Therefore, this negated conclusion must be wrong, so n must be even. And that's what we were trying to show. So direct and indirect proofs tend to feel very different from each other. And for a given problem, generally one of them seems to flow very nicely and the other one feels like it's not really going anywhere. Sometimes they both work well. Sometimes on a really bad problem, neither of them seems to work. But usually there's a preferred direction to a lot of these theorems that will make an indirect or a direct preferable. And you have to experiment. If you're trying a direct proof and you don't feel like you're getting anywhere, try an indirect proof. On the upcoming homework, you get to do both. There's a set of problems you're going to prove, and you have to do them both directly and indirectly. But in a more general setting, if you get to choose, usually you figure out as you work with it which one's going to be more successful. So the way I like to think about this is the way I've been describing it, right? Assume the conclusion's false, argue till you get something ridiculous, which means the conclusion must be true. Because if it's false, this ridiculous thing happens. But there's a more rigorous way to understand an indirect proof. If this helps you, great. If it doesn't, ignore it. Suppose we're trying to prove if P, then Q. So we start off with P, that's the hypothesis. And then we assume not Q, that's the negation of the conclusion. And then we do other things and we get a contradiction. What we've really done when we got a contradiction is we are proving false. In other words, everything I write is a proposition that is true. So the conjunction of any of these is also true. Well, n squared is even is a true proposition, and n squared is odd is a true proposition. So I've proven this and its negation. But we know that a proposition and its negation is always false. Right? We know that x and not x is logically equivalent to false. So if I'm able to prove a contradiction, if I'm able to prove this and this are both true, I've proven false. So when we do an indirect proof, we're really doing a direct proof of false. Well, what does it mean to prove false? I mean, it seems absurd, but it's just a proposition, right? What we've really done is we've shown if not Q is true, then false is true. If we take the contrapositive of this, we know we get something logically equivalent. We know that if this is a true statement, then this is also true. And not false is true, and not Q is Q. So in doing this indirect proof, we're actually proving that true implies Q. And we know that true is always true, so if we put these together, that proves Q. So this indirect proof that leads us to false is really a direct proof that Q is true, but we're proving the contrapositive of true implies Q. We're proving not Q implies false. So I don't know if that helps or not. When I first learned about this, I just kind of thought of it as, you know, prove that the sky is blue. Well, if the sky was green, then, the ocean would be green, and it's not. So sky can't be green. Um, but if you want the more rigorous way of thinking about indirect proofs, that's it. So let me toss out a really clever indirect proof. This was discovered by the Greeks many centuries ago. And I don't think there's a lot of insight in this proof as to how somebody came up with it. But the nice thing about proofs like this is you don't need to know that insight. To come up with a proof, you need some kind of, spark that says, oh, I know how to show this. But once somebody has created a proof, if you can follow it step by step, you can get to the same conclusion they did. And so let's prove square root of 2 is irrational. So remember, a rational number is the ratio of two integers. So in other words, you can't write square root of 2 equals a over b, where a and b are integers. So, I mean, what is the square root of 2? It's 1.414213,562, et cetera, et cetera, right? So, I mean, 1,414 divided by 1,000 gets you pretty close, right? That's almost the square root of 2, but it's not exact. And the Greeks, they studied whole numbers and integers, and they thought you could understand everything like that. And they knew that if you had a 1 by 1 square, that the length of this, if we call it x, was something whose square was equal to 2, 1 squared plus 1 squared. And they wanted to know, well, what exactly is this length x, this diagonal of a 1 by 1 square? What fraction is it? Is it 14 over 10? Is it 28 over 20? Is it 141 over 100? How do we write it exactly as a fraction? And what somebody discovered was you can't do that. So here's a proof that you cannot write the square root of 2 as a ratio of two integers, and it's an indirect proof. All right, so and I'm not going to write it out with all of the steps. Basically, every step's going to be algebra. So let's start by assuming square root of 2 equals a over b, where a and b are integers. And I'm going to add one more assumption. A and b have no common factor. Except, the obvious ones, plus and minus 1. In other words, a over b is in simplest form. So if both of these are multiples of 3, divide them by 3. If they're both even, divide them by 2, so that it's in simplest form. Everybody with me? So we're just going to do some algebraic manipulation. Square root of 2 equals a over b. So 2 is equal to a squared over b squared. And so 2b squared is equal to a squared. So a squared is twice an integer, which means a squared is even. Well, we just did a proof that if a squared is even, then a has to be even. So a is even, which means a equals 2 times k, where k is an integer. So a squared equals 2k squared equals 4 times k squared. But a squared is also equal to 2b squared. Divide both sides by 2. 2 times k squared is equal to b squared. Well, b squared is twice an integer, so b squared is even. And so by the proof we did a few minutes ago, b is even. Well, we've proven that a is even and b is even, which means they have a common factor, which is 2. And that violates our assumption that a and b have no common factor other than 1. So that's a contradiction. And therefore, square root of 2 is not equal to a over b. And that's it. So that's a really good example of a proof that really doesn't leave you with kind of an intuitive understanding of why the thing you're trying to prove is true. At least for me, right? This does not convince me that I can never find two integers whose ratio is exactly square root of 2. I don't get that from here, but I have to believe it's true because each step follows from the step before it. Right? So this is the nature of mathematical proof. It does not need to leave you with some insight as to why something is true, but it leaves you in a place where you cannot deny it. All right, so let's eyeball the homework. So two sections with problems, 3.4.2 number 2. This is a relatively simple problem about fallacies. And then 3.5.4, these are the three problems you're going to do direct and indirect proofs on. So let's look at the fallacy problem first. So question 2, show that the common fallacy, this is not a law of logic. Do you remember what fallacy this is? We talked about two of them. Yes, exactly. That's denying the hypothesis. So this says if P, then Q, P is the hypothesis. And then if we also deny the hypothesis, say the hypothesis is false, then we get a fallacy. So you want to prove that this is a fallacy. In other words, show that this does not always imply that. So you can do this with truth tables. You could do this with particular propositions P and Q. And you only need to show one case where this left side fails to imply this right side. If you can find just one case where that's true, you've proven that this is not a law of logic. Generally, that's easier than trying to prove something is a law of logic. All right, so that's the question from 3.4. 3.5, you've got three questions to work on, 2, 4, and 6. 2 is proving these things with truth tables. 6 is a word problem that you want to prove is either true or not true. And then 4 is these three theorems that you're trying to prove. And for each one, I want to see a direct proof and an indirect proof. So this is the bulk of the homework. So a reminder, when you see something in the book which has a bunch of things with commas and then this double arrow and then something else, it means these three things taken together is the hypothesis. In other words, if A and B and C, and then the thing on the right of the arrow is the conclusion, then D. So please don't confuse that. Don't try to prove that not R implies not P, or that P implies R, or that not C implies B. Prove that if P implies Q, and not R implies not Q, and not R, all of that together, then we have not P. Right? So everything to the left, that's your hypotheses. The thing to the right, that's your conclusion. And you want to do this with a direct proof. So start off with these three things in this case, use the various laws of logic, and eventually come up with not P. That's a direct proof. And then do an indirect proof. And be careful with the indirect proof. To do a genuine indirect proof, you need to start off by assuming P and then using P to argue to a contradiction. Don't just start with these, prove not P, and then claim P contradicts that. That's just a direct proof. Start off with the negation of this P and use it along with these to find a contradiction. Same thing here. Start off with not B, use that along with these hypotheses to find a contradiction. Start off with not B, combine those hypotheses with not B to reach a contradiction. All right, this is not a 5-minute homework exercise unless you've been doing proofs for a while and are very comfortable with it. This takes a lot of time, a lot of thought, a lot of trial and error. Get yourself, a nice scratch piece of paper, good pencil and eraser or a whiteboard or something, and start thinking about how can I put these together to eventually get to not P? Or how can I put these together to eventually get to R? We've done a few of these in class. This chapter is filled with examples, though. So if you're stuck, go back and look at some of the first examples. Right? So for example, here's a theorem. P implies R, Q implies S, P or Q all together implies S or R. And here's a direct proof. And it looks like our proofs we've been doing. There's a step number, there's a proposition, and there's a justification. Premise is what they say for hypothesis. Right here, we take proposition one and we use the conditional rule. Well, that's conditional equivalence. So they have slightly different names for some of these. Premise, that's a hypothesis. This, not P implies S, follows because of propositions 2, 3 in the chain rule. Right? They took not P implies Q, Q implies S, and they chained them together and got not P implies S. So they wrote that down. And instead of writing QED, they draw a box at the end. So same thing. It says this is the end of the proof. They're trying to prove S or R. The last statement of their proof was S or R. That's what they were trying to show. So then they draw a box there. All right. And reminders here, you've got to have a number for each step. It's got to be either a hypothesis or a proposition that comes from the previous steps. The last step must be the conclusion of the theorem. The justification should explain why each of these propositions is true. Put numbers in here so you can refer to them in the justification. And then here's another example where they have a new theorem and they show you two different direct proofs. So there's a lot of examples in here. And then they do the same thing with indirect proofs. So don't just read those, right? Once you read it, you can't do it on your own. And the goal is to get some exercise here. So try doing questions 4 first. And if you're stuck, go back and look at one of these direct examples. And then go back and try to do these questions with direct proofs. If you're still stuck, you can go to question 3. The odd questions have answers in the back. So there's 5 more examples of theorems with direct and indirect proofs. But again, don't just go to the back of the book and read those, because once you read them, you can't actually use them for practice. Once you've seen the solution, you can't challenge your brain to come up with a solution on its own. So use these tactically, right? If you're really stuck, if you're not getting anywhere, pick one problem and take a look at maybe the first few steps. See if you can get through more than you were able to get through, and then use that to advance your own proof. And of course, office hours. Great opportunity to come by and work through these things with me. Or, come to class Monday and ask questions about these, and we can get as specific as you need. All right, questions about that, about what you're going to do. All right, so we're going to switch topics and go into some number theory. Let's do a 5-minute break now, and then we'll come back and we'll start on the next unit. And talk about number theory for a week or so, and then we'll come back and do more logic next week or the week after. So I'll see you back in about 5 minutes. All right. I don't know why the chat window is making my Zoom icon get a little notification count. I think I'm going to worry about it. All right. Last call. Any questions on this stuff? I mean, you can still ask afterwards, but before I move on. All right. Closing that out. So, next thing we want to talk about is called number theory. Number theory is literally the study of numbers. And by numbers, we generally mean whole numbers, integers. Sometimes even just positive whole numbers. So, there's a study about numbers. I mean, you add them, subtract them, multiply them. It doesn't necessarily feel like that big of a deal. Um, but it turns out that even just thinking about integers and thinking about simple operations like multiplication, there's a lot of interesting things that come out, and there's a lot of unknown things that come out. So, so who can tell us what a prime number is? Number only divisible by itself in one. Perfect. So, for example, the number 7 is only divisible by itself in one. The number 23 is only divisible by itself in one. The number 24, as you did in a homework problem, what's got a lot of factors? 2, 3, 4, 6, 8, and 12 are all factors of it. But you go just one number before 23, the only number that divides that is 23 and 1. So what's the difference between these numbers? Why does one number have so many factors and the other one has so few? We don't really know a good answer to that. So people have studied this for thousands of years. Um, Things like when does one number divide another, or when does no number divide a certain number, or when does the number have a lot of divisors? Um, and these simple questions turn out to have implications for things like theoretical physics, um, geometry of higher dimensional spaces. They have some surprising connections to things like cryptography. Um, and in the 70s, people started looking at better ways to do cryptography. And a lot of the things we do today on the internet are only possible because of some of the results of number theory, many of which we're going to study over the next week. And a lot of that's related to prime numbers. So, divisibility is sort of key to what we want to talk about because we're mostly thinking about, adding, subtracting, and multiplying. Well, we know we've got closure under that. Division is weird though, right? 6 divided by 2, no problem. 7 divided by 2, can't do that if we're just dealing with whole numbers. So, we're gonna start by talking about divisibility. And let me give you a definition. So, a number A is divisible by B if there exists an integer k such that A equals B times k. So for example, 21 is divisible by 7 because 21 equals 7 times 3. So A is divisible by B if there's an integer that when you multiply by B, you get A. In other words, if we allow ourselves to divide things like real numbers, A divided by B is an integer. And we have some other equivalent statements to A is divisible by B. We would say B is a factor of A. We would say A is a multiple of B. And we would also say B divides A. When we say B divides A, we mean divides it evenly, right? A whole number of times. And this is the form we'll most often talk about. And we have a shorthand for this, which is B, a vertical pipe, and A. So this means B divides A. It's a totally different notation from what we've done before. And this is not B divided by A. This is not an operation. This is a proposition. B pipe A, that's a proposition. It's a declarative statement that B divides A, that A is a multiple of B, that B is a factor of A, that there exists an integer K such that A equals B times K. Those are all equivalent propositions to this, B vertical bar A. So when you see this, it's a proposition, declarative statement with a truth value. It's not a mathematical operation. It's not saying take one number and perform a division operation. It's stating that if you take A and divide by B, you get a whole number. Everybody clear on that? So we can make some statements about divisibility. So here's a theorem. And just assume everything is an integer until we say otherwise. So for what I'm about to write, A, B, and C are integers. So if A divides B and A divides C, then A divides B plus C. For example, 3 divides 15 and 3 divides 30. And also 3 divides 15 plus 30, which is 45. In other words, if B is a multiple of A and C is a multiple of A, their sum is a multiple of A. You could prove that pretty easily just by using this definition, right? If A divides B, B is equal to A times some integer K1, and C is equal to A times some other integer K2. So B plus C would be equal to A times a third integer, K1 plus K2. So you can take this definition and you could show this pretty easily. We'll take this as given. So if A divides B and A divides C, A divides B plus C. If A divides B, then A divides 2 times B. And that should make sense, right? If I can divide B by A, I can take 2 times B and divide it by A. I could also take 3 times B and divide it by A. I could also take 175 times B and divide it by A. In fact, I could take any multiple of B and divide it by A. Also, if A divides B and B divides C, then A divides C. And these are just slightly formal ways of saying things that you probably already know if you think about it. If B is a multiple of A and C is a multiple of B, well, C is also a multiple of A, right? C is B times something, B is A times something, so C is A times something. So divisibility has some nice properties that we're going to take advantage of. And the way we're going to take advantage of it is a theorem, but it's actually called the division algorithm. But it's a theorem. So I can give you a very formal statement of this theorem, and it's going to involve a lot of words and not a lot of insight, and I don't want to do that. So let me explain to you with some examples what this theorem is saying. And then if we have questions, we can make it more rigorous. But suppose you take two numbers. For example, suppose you take the numbers 17 and 3. And I try to do a division. I try to do 17 divided by 3. And suppose I don't know about fractions, I don't know about decimal numbers, I don't have a calculator. When you first learn about dividing numbers, and someone says divide 17 by 3, what would you do? Well, let's start with instead 15 divided by 3. So what's 15 divided by 3? The warm up. Good. So 15 divided by 3 is 5. Okay, if I do 17 divided by 3, I get 5, but I've got something left over. I've got what we used to call in school a remainder. So you would say 5 with a remainder of 2. Everybody familiar with that? Right, it's the leftover stuff. This is 5 with nothing left over, so it's 5 with a remainder of 0. So if I wanted, I could write this as 5 with a remainder of 0. 16 over 3 is 5 with a remainder of 1. 17 over 3 is 5 with a remainder of 2. 18 over 3, that goes in exactly 6 times with a remainder of 0. 14 over 3 would go in 4 times with a remainder of 2. So no surprises so far, right? So the division algorithm says that if I take two numbers and I divide them, I can write it as some whole number quotient and a remainder. And in this particular case, my remainder is always going to be bigger than or equal to 0 and less than 3. And it's less than 3 because I'm dividing by 3. So the first part of this theorem says if I take two numbers and I divide them, is somewhere between 0 and something less than what I'm dividing by. If I were to divide by 7, like 21 divided by 7 is 3 with a remainder of 0. 24 divided by 3 is 3 with a remainder of 3. 27 divided by 3 is 3 with a remainder of 6. Sorry, divided by 7. 28 divided by 7 is 4 with a remainder of 0. 20 divided by 7 was 2 with a remainder of 6. And so in this case, I can write my division as a whole number with a remainder. And the remainder is bigger than or equal to 0 and less than 7. And it's less than 7 because that's what I'm dividing by. So the division algorithm says I can always do this. I can take two whole numbers and write that division as a whole number with a remainder with this property. It also says that that result is unique. There's exactly one way to write a quotient as something with a remainder where the remainder has this property. All right, does that make sense? So I can give you the formal version of this, but I would prefer you think about it like this. But let me just give you a formal version. So let A be an integer and let D be a positive integer. Then there exists a unique quotient and remainder in the set of integers where the remainder is bigger than or equal to 0 and less than D, such that A is equal to your divisor times your quotient plus your remainder. So if you want to know the mathematics of it, that's the formal definition. But for practical purposes, think about it like this. Take two numbers and divide them. There's a unique way to write it as something with a remainder where the remainder satisfies that property. All right, good so far? So 17/3 was 5 with a remainder of 2. I could also write it as 4 with a remainder of 5. Right? 3 goes into 17 4 times. that gets me to 12, and I've got 5 left over. Or I could say it goes in 3 times, that gets me to 9, and I've got 8 left over. Or I could say it goes in no times, and I have 17 left over. Or I could say it goes in -1 times, that gets me to -3, and I have 20 left over. Or I could say it goes in 6 times, and I have -1 left over, right? 6 times 3 is 18, and I've got an extra -1. So all of these are true statements. The division algorithm says there's exactly one case where our remainder will be non-negative and less than 3. That's this case right here. So we can talk about the remainder of 17 divided by 3. And when we just talk about the remainder, when you do a division, we're talking about the remainder that satisfies this property. The division algorithm says that always exists and it's unique. So you'll have some homework questions later that ask you to find the remainder when you do certain divisions. That's what we're talking about. And this number on the bottom is always going to be a positive integer, but the number on the top could be negative. For example, if I do -5 divided by 3, I want to write that as something times 3 plus some remainder. Well, it could be 0 times 3 with a remainder of -5. It could be 1 times 3 with a remainder of -8. Or it could be -1 times 3 with a remainder of -2. Or it could be -2 times 3 with a remainder of 1. Or -3 times 3 with a remainder of 4. Right? If I take -3 times 3, that's -9. And if I add 4, I get to my -5. If I take -2 times 3, that's -6. And if I add my remainder of 1, I get to my -5. If I take 0 times 3, that gets me to 0. And I take my remainder of -5, that gets me to -5. So I can write this a number of different ways. But if I want to know what the remainder is when I divide -5 by 3, I look at this, and the remainder is 1. So this is a good time to ask, why do we care about this? What's so interesting about remainders? And the answer is there are calculations that we do in computer science and other places where the remainder is more important than the whole part of a division. We're interested in the leftover part. For example, suppose it's 8 o'clock and you want to add 7 hours. And you want to know what time is it going to be in 7 hours. Well, 8 plus 7 is 15. And if you do military time, you can say it's 1,500 hours. That's fine. But if you want a number of hours that's 1 to 12, what we can do is we can take this 15 and divide it by 12, and we get 1 with a remainder of 3. It's going to be 3 o'clock. The reason being, when you've got a clock face, you've got 12 hours, you can move forward 1 hour and your time goes up by 1, or you can spin around 500 times and then move forward 1 more hour and your time still goes up by 1. So if you want to know what time it's going to be 700 hours from now, you really don't care about most of that 700. You'd like to know, when I go up 700 hours, how far do I move on this dial from 0 through 12? And if we did 700 divided by 12 and found what that was, cheat and use a calculator. So this goes in 58 times with 4 left over. So if it's 8 o'clock right now and we wait 700 hours, it's going to be 12 o'clock. So we already use modular arithmetic in some cases. And telling time is sort of the classic example. But there's other things we do in computer science, for example, when we do crypto systems, when we compute hashes for identifying large binary files and authenticating them as original. These all involve modular operations. Adding, multiplying, things like that, where we only care about the remainder after some sort of division operation. So we're mostly going to talk about modular arithmetic. So more definitions and terminology. So we say A is congruent to B modulo M, and we write it like this. This is the case if M divides A minus B. So if two numbers A and B, if their difference is divisible by M, we can say A is congruent to B modulo M. So for example, 17 is congruent to 8 modulo 3. Why? Because 17 minus 8 is 9, and that's divisible by 3. Right? 3 divides 17 minus 8. All right, somebody give me another number that 17 is congruent to modulo 3. Right, 17 is congruent to 2. Perfect. Right, because 3 divides 17 minus 2. 17 minus 2 is 15. That's a multiple of 3. So 17 is congruent to 2. Excellent. Well, it turns out 8 is also congruent to 2 modulo 3. Because 8 minus 2 is 6, and that's a multiple of 3. So there's what we would call a transitive property, right? If 8 is congruent to 17 and 17 is congruent to 2, then 8 is congruent to 2. And that's always the case. So we have this property. If A is congruent to B and B is congruent to C, then A is congruent to C. And just suppose this is all modulo some fixed number M. All right, we have another property. If A is congruent to B, B is congruent to A. And that should make sense if you think about it a little. If we say A is congruent to B, it means M divides A minus B. Well, if M divides A minus B, then M also divides B minus A. If 15 is a multiple of something, so is negative 15. You just throw an extra minus sign in front. And if M divides B minus A, that means B is congruent to A. So this really follows from that. So we know this is true. There's an even simpler fact which is true. A is always congruent to itself. And why would this be true? How do we show that that's true? What's the logic there? Everything can be divided into 0 to get a remainder of 0. You can't actually divide by 0, but to say A is congruent to A, modulo M means M divides A minus A. Well, A minus A is 0. This is saying M divides 0. Yeah, you're fine. And everything divides 0, right? To say M divides 0 means there exists an integer k such that 0 equals M times k. Well, the integer 0 works great for that. So as long as m's not 0, right, this is always the case. So we have this third fact that every number is congruent to itself. Well, these three facts taken together are particularly powerful. We have what's called a transitive relationship. If A is congruent to B and B is congruent to C, then A is congruent to C. We have this commutative nature. If A is congruent to B, B is congruent to A, and we have what's called a reflexive property. A is congruent to itself. And if you take these together, if you have all three of these, we would make the following statement. This congruence operation is what we call an equivalence relation. Don't worry about what that means. But the punchline when you have an equivalence relation is you can use it to break things into buckets. And so in our case, let's just think about modulo 5. we can take any number and we can say, what is this number congruent to modulo 5? And if we take all of our integers, they're going to divide into 4 groups. A group of things congruent to 0, a group congruent to 1, 2, 3, and 4. Any number we think of is going to fall in one of these 5 bins. So this is what equivalence relations do. We would say formally they partition a space into subspaces. In this case, modulo 5 is a notion that breaks our set of integers into 5 bins. The reason this is useful is because if we want to study something about all numbers, that's a lot of numbers to work with. If we can shift over to thinking about what numbers are congruent to modulo something, we may have to work with fewer things. For example, if we're working modulo 5, we only have to work with 5 things. This bucket, this one, this one, this one, and that one. And it may be possible, for example, to prove certain things using these ideas of modular arithmetic. So let me give you some more properties, and then we'll explore that. So if A is congruent to B and C is congruent to D, then A plus C is congruent to B plus D, and A times C is congruent to B times D. So you only need one of each bucket because everything else is equal to one of those. Yep. And this is going to be a big property that we take advantage of when we want to do large calculations for doing encryption, for example. So if I know 2 things are equivalent to each other, I can kind of use those things as representatives for a larger group. As long as I'm just thinking like, modulo M. If A is congruent to B, A is as good as B. I can kind of use them interchangeably. So, for example, what is the remainder modulo 5 of what's the remainder modulo 5 of this product? Well, I could multiply these numbers out, take the result, divide by 5, see what I have left over. But I can do something simpler. I can say, what's the remainder when I divide 17 by 5? Well, 17 is 15 plus 2. So this is congruent to 2 modulo 5. 21 is 1 more than 20. So this is congruent to 1 modulo 5. 11 is also 1 more than 10. So this is congruent to 1. 51 is 1 more than 50. So this is congruent to 1. And 18 is 3 more than 15. This is congruent to 3. So this will be congruent to 2 times 1 times 1 times 1 times 3, which is 6, which is 1 more than a multiple of 5. So if I know what these are congruent to, I barely had to do any work. Whereas if I were to multiply these out, it would take, a calculator or a number of lines on a piece of paper. Let me give you another example. But I'm going to say don't do this for propositional logic homework. You're going to have questions like this in your chapter 3 stuff. You're not allowed to do this for those. But suppose we wanted to prove if n is even, then n squared is even. Well, if n is even, what is n congruent to modulo 2? If n is even, what's it congruent to modulo 2? Yeah, it's congruent to 0. In other words, if I take n and I divide it by 2, there's nothing left over. That's what we mean by being even. It's twice an integer. Well, n squared is n times n. That should be congruent to 0 times 0, which is just 0. And if n squared is congruent to 0 mod 2, n squared is even. Because that means if I divide by 2, there's nothing left over. So there's a really, really short proof that if n is even, n squared is even. And by the same token, if n is odd, then when you divide by 2, you have 1 left over. So n is congruent to 1. N squared is congruent to 1 squared, which is just 1. So n squared is odd. So those proofs that take a page of writing using propositional logic, they're trivial facts under modular arithmetic. But don't do that on your homework. All right, here's another example. Here's a big, long, semi-random number. I want to know if it's divisible by 3. Well, if I have, you know, a Linux machine available, I can do 42113160 divided by 3, and it does not go in evenly. It looks like it's got, oh, I typed it wrong. 42113160 All right, that goes in evenly. I had my first digit wrong. So yes, this is divisible by 3. Um, and I wrote that number down specifically because it was divisible by 3. So how do you know this is divisible by 3 without actually doing the division? Anybody know the trick? It's a good party trick, depending what kind of parties you go to. Let's just look at the number 351. So this is actually the number 1 plus 5 times 10 plus 3 times 10 squared. I could keep going. Suppose I want to know, is this number divisible by 3? Well, that's the question. What is this congruent to modulo 3? So 351 is congruent to 1 plus 5 times 10 plus 3 times 10 squared modulo 3. Well, what is 10 congruent to modulo 3? What's the remainder when you divide 10 by 3? 1. Thank you. Right? It's 1 more than a multiple of 3. So 5 times 10 is congruent to 5 times 1. And since 10 is congruent to 1, 10 squared is congruent to 1 squared. Well, 5 times 1 is just 5. 1 squared is just 1. 3 times 1 is just 3. So 351 is actually congruent to 1 plus 5 plus 3. In other words, the sum of the digits. And if I had another digit, 0 times 10 cubed plus 6 times 10 to the fourth plus 1 times 10 to the fifth, each of those powers of 10 is just congruent to 1. So this original number is congruent to 4 plus 2 plus 1 plus 1 plus 3 plus 1 plus 6 plus 0 plus 3 plus 5 plus 1 modulo 3. So if I add up these digits and I get something that's a multiple of 3, the whole number is a multiple of 3. So that's a cheap party trick. If you want to know if a number can be divided by 3 evenly, just add up the digits. It also works for divisibility by 9, which is why when you look at multiples of 9, when you add up the digits, you always end up with 9 or a multiple of 9, right? That's because 9 is congruent to, or 10 is congruent to 1 modulo 9. So if I work mod 9, exactly the same trick applies. All right, so we'll look at more applications of this next week, but let me wrap up with one more um, observation about modular multiplication. So when you learn to multiply in school, you get a multiplication table, and it's got numbers going across the top and numbers going down, and then in each row column intersection, there's the product. And so I think in my school, we went up to 12 by 12. Some aggressive schools go up to 20 by 20, right? But you memorize this table or you try to memorize it. Um, and that's great for multiplying small numbers, but it doesn't help you if you want to multiply, 5,216 by 185. You've still got to do long multiplication. But if we work modulo something, for example, modulo 5, all we need is that one multiplication table, and that tells us everything we need to know. So I'm going to ignore 0 because we know 0 times anything is just 0. So let's just work with our other possibilities, 1, 2, 3, and 4. And this is doing multiplication. So 1 times 1 is 1. 1 times 2, 3, 4 is still just 1. 2 times 1 is 2. 2 times 2 is 4. What about 2 times 3? What is that modulo 5? Thank you. 2 times 3 is 6, which is one more than a multiple of 5. And 2 times 4 is 8, which is 3 more than 5. And so we can fill this in. Like that. And there's our whole multiplication table. So now if someone asks you what's 2 times 3, you can just say 2, 3, it's equal to 1, or congruent to 1. So that's multiplication modulo 5. Let's look at modulo 4. So 2 times 2 is 4. That's got no remainder when you divide by 4. 2 times 3 is 6. That's got 2 left over. 3 times 2 is 6. That's got 2 left over. 3 times 3 is 9. That's got 1 left over. So there's two examples of multiplication tables. One modulo 5, the other one modulo 4. There's a significant difference between these two tables. There's a few differences. The most significant is this. There's a 0 in this table. And there's no zeros in this table up here, modulo 5. There's also repeats in this row. There's no repeats in any of these rows, and there's no repeats in any of the columns. And because there's no zeros in this table and there's no repeats, every number appears in each column and in each row. Different orders, but every number can be found in here. There's a 1, 2, 3, 4. Not the case here, modulo 4. For example, there's no 1 in this second row. So there's something fundamentally different between this table and that table. And the reason that we have this difference is because 5 is a prime number and 4 is not. And if we do this for any number, 17, 21, whatever, we're going to see the same behavior. If we make a table for multiplication modulo a prime number, we have no zeros, no repeats. Every number appears in every row and column. If we do this modulo something that's not prime, we lose that pattern. We end up with some zeros, some rows where things are missing, some repeats, and so on. So this is a subtle way that prime numbers start to pop into things. And it's one of the reasons why prime numbers are so central to doing modern cryptography. So the whole thing that makes commerce work on the internet is the ability to generate large prime numbers, large as in a few hundred digits. And the fact that multiplication modulo these primes has this kind of property set as opposed to that. All right, that's a kind of whirlwind introduction to the subject. We'll get a little more, a little less abstract as we go forward from here. But that's the building blocks of what we're going to be doing. I'm going to let you out about 4 minutes early with all of that. Take a look at the homework 3 problems. Come to office hours Monday if you got questions, or if not that, come to class on Monday and ask questions about the homework. And I will see everybody next time. Have a good rest of the day. Thanks.
Thank you.
You're welcome.